lesson on the motor effect. You need to have seen the previous ones about electromagnetism, and now we're going to join it all together in motor effect. Bear in mind that this has a lot of diagrams, and some of mine might not be the best. However, bear with me and see if you can understand what I'm on about. Okay, right, let's just remind ourselves of two types of fields. One of them is a nice north and south magnet. Here's a north. It's slightly different to the bar magnet we're familiar with, and the south is on the other side, so I sort of do it as a dotted line as a south. And I'm sure you can remember here, the field lines go from north to south, and so we have what's built up a really nice straight, what we call a uniform magnetic field. Okay, and we're going to make use of this when we're dealing with motors. In addition, we're going to look at a piece of wire, and we're going to look at it carrying a current carrying piece of wire. And you should remember from your previous lessons that the right-hand grip rule means that we're going to get magnetic fields going around this piece of wire. Which way do they run? Well, if you imagine your thumb is the current, your finger should indicate the direction of the magnetic field. So here they are, all the way around. Okay, now that's it's going to get really complicated if we draw three-dimensionally all the time. So hopefully, when I draw like this, you'll know what I'm referring to. And when I draw like this, you know that this little dot means the current's coming out of the page. And I can draw the magnetic field lines around. So hopefully we can remind ourselves, this is three-dimensionally. But to make things easier, we might draw two-dimensionally. So I hope you know which is which. Okay, now let's try and combine the two. Let's have our static magnetic field. Sorry, our uniform magnetic field, should I say? The north there, and I shall place one in with a south. And inside there, we're going to place this piece of wire, gigantic piece of wire by the look of things, nonetheless, a piece of wire with a current flowing. Okay, so let me just draw in those field lines again. We've got north versus south moving this way. And indeed as well, you also have a magnetic field around the wire. So if I were to draw them, let's just draw them in just a little bit more permanently. Now, there's one thing about magnetic fields is you can't have both of them. They either add together or they disappear. What you'll notice at the bottom here, they're going the opposite direction, and the top they're adding up. So at the bottom there, going away from each other, and the top they're adding up. So what does that leave us with? Well, all the ones at the top will start to disappear, and all the ones at the bottom will start to... Sorry, that's the other way around. It's going this way and that way. Now, like I said, in 3 dimensions it's going to look a bit of a mess, so therefore let's draw it in 2 dimensions and see what we've got going on. There it is. The current is coming out of the page. It's coming up and following the pen. We have those with magnetic fields going this way around. And indeed, the permanent magnets have magnetic fields that are going this way. So at the top, you see here, there's a cancelling out, whereas at the bottom here, you see it's strengthening. And with those strengthening, it leaves us with a resultant field that actually wraps around the magnet. Sorry, around the piece of wire. Okay, so let's just look at that finally as one nice diagram without all the fields interacting. Here it is. the fields wrap around the wire, and they cause the wire to experience a force. Now that should make sense to you, because in effect what we've got is we've got one magnet and another magnet, and when two magnets come together they either repel or attract, so they can create a force. So here you actually have the direction in which that force is acting. And the way that we work out the direction of the force is through something called the left-hand rule. Fleming's left-hand rule. And what it does, it makes use of the left hand. I'm going to draw a terrible hand here. But it's going to be a hand that's gripped like a fist. Try and add a little bit of detail to this. So here is our thumb. This is our first finger. And this is our second finger. And the way that you hold them is you hold them in 3 dimensions. You hold one up, one across, and then one coming out towards you. So imagining now, using my own hand here, here is my thumb, this is my first finger, and this is my second finger, and you hold them 3-dimensionally, all at 90 degrees to each other, as if you were drawing an X, Y, and Z axis. And what you can do is you can use that to find out the direction of the force, because what we need to have is, we need to use each finger to indicate something different. So our first finger, because it starts with an F, is the field lines. The second finger with the C is the current. And the thumb, the T, is the thrust, or the force. So if we were to use this example that you can see here, and let's just imagine we align my first finger with the field, which goes north to south. My second finger is the current, and because it's a dot, it's coming out of the page, up. Therefore, my thumb indicates the thrust, or the force, which is going up. Okay, there are 2 ways to change the direction of the force. If I was to change the direction of the current, go into the page, the thumb indicates that the force comes down, and if I was to change the direction of the magnetic field, but not change the direction of the current, my thumb indicates the direction of the force. So really, the left-hand rule helps you out of trying to picture 3-dimensionally what's happening here. So let's just do reverse the force. There are 2 ways. Number 1, reverse the current. And number 2, or should I say, reverse the magnetic field. And I suppose if you do both of them, one in succession, you come back to the original one. However, bear that in mind. Fleming's left-hand rule, or the left-hand rule. Thumb is the thrust, first finger is the field, second finger is the current. And you'll see how they become very, very useful later on. Need to say as well, if we want to increase the force, then there are 2 things that we can do to increase the force. One would be to increase the magnetic field. And the second one would be to increase the current. Of course, increasing the current increases the strength of this magnetic field about the wire. So it's all about increasing the magnetic field. Okay, why is this so important as opposed to just being a little bit of a trick? Well, it's really important because now we're coming on to motors. Even trickier diagram. However, here is the bit that we've been waiting for. And that is a very simple motor. Motors have got far more advanced these days, but they still operate on the same principle. And that being that you have, rather than just one piece of wire, you have two bits of wire, and they rotate on an axle. The pieces of wire are wound consecutively, so the current will flow through one direction, and then across, and then back up the other side, and keep going around. And that is all placed inside a nice uniform magnetic field. So this is a very simple setup of a motor. Now, before we actually get to the operation and how it works, maybe it might be an idea to suggest how do we create the currents flowing along those wires. Well, for that you need to take this part and just take a look at it a bit more closely. Along the axle there is wire which attaches to these slip rings. So say this one attaches to there. And what we have is we have something permanently resting against those slip rings as they then go around the coil. So lots of wires, lots of wires. Now these will be attached to a battery of sorts. They're permanently resting, so as this rotates either way, you're not getting wound up, but this is just touching and making contact. These are known as brushes. And these are known as slip rings. And you need to be familiar with those terms. Okay, it's getting pretty complicated in the 3D diagrams, so therefore let's move to a 2D diagram and think about what's happening or to how to create rotation. Motor is looking at something moving around and around and around. Okay, we're going to do 3 of these diagrams side by side. Slight different times of rotation in each of them. Right, inside we're going to show our axle, and here are our 2 bits of wire. We are going to have a north-south. These are staying permanently attached. They are not changing. There is our axle. And the bits of wire, of course, are going to have a current flowing through in a certain direction. Here is a dot, implying it is coming out, and here we have a cross, which implies it's going in. Okay, let's look at the left-hand rule in this instance. Here is our axle. What's going to be the direction of the force on this side of the coil? Well, let's think about this. If we use our left-hand rule again, we have our field, which is going north to south. We have our current, which is coming out, implying for the thumb, the thrust is going up. So here is our force. And very simply, we talked about how to change the direction of the force, and the only thing that's different in the second one is that we've changed the direction of the current. So therefore the force is acting down, causing a rotation. Okay, now what happens when we get to the top? We still have our actually I'm going to differentiate these two by doing this on a dotted line. So we still have our current coming out, and we still have our current here going in. So the forces will still be the same. However, there's nowhere for it to go. So this actually stops. And that's something we don't want to happen. We don't want the motor just to turn a quarter turn and then stop. How could we continue it? So what we want, ideally, we require somehow what we want to happen is still this axle. We want, rather than it being a dot, current coming out, we want to change the direction of the force to be down, So we need the current to change direction. And similarly here, which was a cross, we want it to become a dot. We require a change in direction of current. So in order to move. Now, how is this achieved? Well, it's achieved by a very useful bit of engineering. And this bit of engineering, I don't know whether it's in the syllabus, but without really understanding it, you don't quite appreciate how motors work. But it's called, so in order for this to occur, so in order to reverse the current, you need a split ring commutator. And a split ring commutator is essentially, if I can try and draw the diagram of this thing moving round, back to 3 dimensions now. If here is our axle, give it some. Then what's happening at this point here is we have half of our cylinder connected to one side of the ring and the other half electrically connected to the other. And that means, and then we have brushes attached to a battery. So as this turns around, as it goes beyond the upright, the brush will touch the other side and create the change in direction of current. A split ring commutator. Let me try and draw that for you, but in 2 dimensions for you this time. We're going to do 4 diagrams. Each with different parts of the rotation. These all remain north-souths. And this time I'm going to draw the split ring commutator large. Obviously our brushes to a battery. And our wire. Okay, just like the first instance. We use our left-hand rule here and we realise that this is going up and that side is going down, hence we get a rotation, just like step 1. As we approach, here we go, piece of wire there, our other piece of wire, still connected, still coming out of the page, still going into the page. Let's connect that to our split ring commutator. And our brushes are still connected, if you see. To the same sides. So we still have that force going up and coming down. Now this is the bit where we get to the top of the rotation. Ironically, what I should have drawn there is no current at all, and no current at all, because the brushes are actually touching neither one side nor the other side. So hopefully, you hope that the wire carries through upright position. Due to momentum. Okay, but there is no driving force. There is a force. There is a force. Similarly, there is a force, but now there is no force on it. But as it continues to go through the top position, you can see that this, which did have the current coming out of the board in each instance, now is touching the other side to that which it was, and now the current goes in. And similarly the bottom side as well, the current is coming in. I hope you can see that, how we've got a change from here to here, and therefore a change of force on these things, so that continues the rotation. Because in order to go through the upright, you're going to have to change the nature of the force, so it goes up, up, nothing, down, down, and that continues and continues and continues. So that, therefore, it becomes a motor. Continually moving. Okay, how do you change the speed? Well, if you want it increased, there are three ways that you can do it. One, you want to increase the magnetic field. Two, increase the current, which in effect is increasing the magnetic field around the wire. Or three, interestingly, the number of coils of wire. Remember I said this doesn't need to be one piece of wire, but it can be many pieces of wire. Many pieces of wire. More wire, more cumulative effect. Now that is a lot of diagrams to take on board. We're going to spend a lot of time in lessons looking at these examples, but I hope you've understood, one, the left-hand rule, essentially left-hand rule, and two, how this magical piece of kit works in the middle. Okay, that's it.